Alright, you guys, so number 9 has a lot of moving parts to it. It's pretty hard, and I think this video will really focus on like the thought process that you might go through. So instead of showing you the answer right away, I'm going to try to sort of show the thought process that goes behind it, just so that we can have like a better understanding of like, okay, what do you do when you face a problem like this? I don't want to show you the answer right away because it's not so obvious right away, okay? So I hope you learn one or two tools down the road. Let's see what happens. So for number 9, we have that the function f is defined by this right here, okay? For these values, okay? So this is technically like my domain or range or something like that. See, so your values can only go from -r up to r. And so if you notice, here's your r. So your function basically is defined from there to there. Okay, that is all it's really telling you. And that the region enclosed by the graph of x equals f of y, and the y-axis is, here's the first big hint, is rotated by 360 degrees about the y-axis in order to form a solid sphere. And so really, and this is more of a big brain thing, like you don't have to notice this, but this is really like the equation of a circle. Equation of a circle, okay? The equation of a circle goes like this. If it starts at the origin, so at the origin, if it's not at the origin, you're gonna like figure out the center and stuff like that. But at the origin, it is x squared plus y squared equals r squared. And so from here, whoever created this problem, all they really did was get x alone. So they did minus y squared, x squared equals r squared minus y squared, square root to both sides in order to get x alone. And that is what they ended up with, okay? This is where that comes from, okay? That comes from this. And so basically what they started with, okay? What they started with was simply this circle that you see here. And then they spun it around a bunch of times. They rotated it 360 degrees. And so basically they replicated the circle and started giving it more of a 3D shape. Now, I'm not exactly good at drawing 3D figures, but I hope you get the idea. So basically, you ended up with more and more circles each time, and then bada bim, bada boom, you ended up with a whole sphere. Okay, now this sphere has a hole in it because they also tell us up ahead that there is a sphere that is drilled through along the y-axis, creating a cylindrical hole. And so here you have two main shapes. Okay, clearly on the one hand you have the solid sphere, and on the other hand you have the cylinder. Okay, cylindrical hole, cylinder, right? And if you do the sphere minus the cylindrical hole, you end up with what they call the spherical ring. Okay, this is the spherical ring, which is basically just a sphere with a cylinder that got like pummeled through it, right? Drilled through it. It subtracted it from its volume. Ah, interesting. And so then they tell us, because apparently this is going to be useful, right? Then they tell us that the spherical ring, okay, has a volume, okay, has a volume of pi cubic units, and through all of this to find the value of h, and h is right here. So of course this is a lot of different information thrown at us, and we have to go piece by piece in order to really understand the ideal process and stuff like that, okay? So the first thing we can really try to like think about or go over is that, okay, I have a couple of shapes here, right? On the one hand, I have this sphere. On the other hand, I have the cylinder. And subtracting both, okay, you end up with a spherical ring. I'm just going to call it ring, okay? So you have the sphere, you have the cylinder, you have the ring, right? And we're talking about volumes here, see? And so technically, as I said earlier, the volume, okay, the volume of the ring has to equal the volume of the sphere minus the volume of the cylinder. Which makes sense because if in this diagram here, right, you go ahead and take the area of the whole like circle or sphere and you subtract this, which I'm putting in red. Okay, so if you subtract all of this, yeah, if you subtract all of this from your shape, you end up with the ring, right? All that I drew in red that I'm colored in red that I was deleting is this whole thing over here, right? This cylinder that shows up like that. That is what you're getting rid of, okay? That is what you're eliminating. So if you eliminate that, you end up with the ring. So that is what I'm telling you. The volume of the ring is equal to the volume of the sphere minus the volume of the cylinder. Now from here, there are a lot of different approaches, you guys. In fact, just looking at the mark scheme quickly, you have one method up here, you have another method over here, you have another method over here. So it's pretty crazy. There's a lot of different ways to solve this problem. It can get overwhelming, see? And so what I would sort of suggest is that, okay, you first established that for the volume of the ring, you got to do the volume of the sphere minus the volume of the cylinder. That is the first big, like massive sort of step. Now, the other sort of thing you have to realize, or the other tool you have to add to your toolbox, okay, is that this is the thing. Integrals are for finding volumes slash areas. Literally. Integrals are for finding volumes slash areas. In fact, when you're dealing with something like a normal distribution, okay, and you want to find the area from here to here, like normal CDF, okay, all your calculator is really doing is doing an integral of this whole thing from here to here. And it spits out this area, and that area is probability. See? So you've been using integrals for finding volumes and areas like the whole time. Maybe you just haven't really realized it. See? Um, so yeah, the integral is marvelous. It's excellent for finding volumes or areas. So in this case, we will be using it mainly for finding the volume, right? Now, what is another sort of way that you can realize or notice that this is the approach? Well, getting familiar with the formula booklet. Guys, the formula booklet has a lot of formulas, of course. It's a formula booklet. There's a lot of stuff in here that you can use that can really save you the day of the test or any test that you ever take. See? And so, in this formula booklet, there's one key tool that I would like to show you. In the topic of calculus, you will find topic 5, see? You will find stuff about integration, derivatives, and all that stuff. And here, this random guy online started talking about derivatives. So, and about integrals, sorry. So it's probably important, see? So let's go to page 11 or 12, right? Well, 12 because HL only, and we're cool boys by now, see? So now that we're part of the cool team, we can look at all these integrals and notice and tell ourselves, wow, why did I ever take Math HL? But you can also say, okay, there's one sort of relevant thing here, which is hidden right there. Bada bim, bada boom. This is the volume of revolution about the x or y axes. And so earlier I drew with my amazing art skills a replication of how this circle is sort of like repeating all along it, right? So it's it's rotating. See, it's rotating, so you end up with one circle there, another circle going like that, another circle cutting through like the middle. You end up with a bunch of different circles. That is how you end up with a 3D shape, right? And so when it says, and here's the big idea, see? When it says that it is rotated by 360, it's actually also telling you, or the equivalent, right, is that it is a volume of revolution, see? So it's also, I mean, really, if it's rotated by 360 degrees, it's like the circle is doing a lot of revolutions. That's the most intuitive way I can put it. The circle is doing a lot of revolutions. Okay, so if it can do a lot of revolutions, if it can spin a lot, right, it rotates by 360 degrees, right? And so suddenly this tool becomes very, very relevant. And I've actually noticed that the IB loves to put in questions about, like, you have this shape, it spins 360 degrees, what's the area? Like, that's their classic. They love to do that, see? And so from here, well, here's my main tool, right? And so for the volume of revolution, let me just write this down. On the one hand, you have one version which is just with like y, and on the other hand, you have a version that's just with x, see? At the end of the day, it's pretty much the same thing, see? Point is, your integral looks like this. So our volume, right? The big tool that we're going to use, which I'm going to put in green, okay, the volume, right? is going to be the integral of from a to b. Yeah, I'll talk about that in a second as well. Pi, okay? And then, I don't think it really matters what we use, but we'll just go pi x squared dy. See? Yeah. So point is, in order to fill this in, we need to clarify what each thing is. See, so on the one hand, this a, okay, is your smallest value. This b is your biggest value. Now you might be thinking, is it x or is it y biggest value? And in this case, because I chose dy, it's going to be the biggest or smallest y value, okay? But that is only because this is the integral in respects to dy. Okay, if it was in respect to dx, it would be a little bit different. See? Now, why did I specifically choose the one of dy? Because we need to find the value of h. Let's not forget, and h is right here, and h works vertically, and so h has to do with y, so we're going to do the integral in respect to dy, okay? And this x squared, I know it looks kind of weird because it's an x, but really this is just your function, okay? It's just your function. And so if you follow all of these sort of approaches and rules, right, for plugging this in, right, well, you have that the volume of a ring, they told us, is just pi, right, from here. So volume of ring equals pi. It's going to equal the volume of sphere, which following this, will go from the smallest value of y, which, what would be the smallest value of y, you guys? And so, because we're talking about h, right, well, this sphere, or all these shapes, start perfectly at the origin, right? They start perfectly at the origin, right? Because, well, they don't really tell you otherwise, and you can also get the hint from here. See? It starts at the origin. And so, really, this right there is half of h, and this right there is also half of h, right? And so what that actually tells you is that down here, this y value is negative h over 2, and this y value is h divided by 2, right? We're talking about y values here, you guys, right? And so the smallest y value that you will be evaluating this integral on is negative h divided by 2, and up here you have h divided by 2, times pi times x squared, and x we said was our function. So our function is up here, right? It's just square root of that whole thing. So it's square root of r squared minus y squared. All of this squared because it's part of my formula, right? And integral respects to dy. So this whole thing was for volume of sphere, right? This is where I'm at, volume of sphere. We do minus the volume of the cylinder, right? Now, for the volume of a cylinder, it's a little bit harder. I mean, more than harder, it's tougher to spot, see? So I'm going to try to go over that in a second. Just give you a moment, see? And so for volume of cylinder, I'm just going to write minus volume of cylinder for now, see? Yeah. So, what the heck do we plug in for the volume of cylinder? Well, on the one hand, I will immediately tell you that we will be using this approach again, but just spotting that approach is a little bit tough. So let me show you how it works, right? So on the one hand, we just found, okay, we just found how to express, all right, we just found how to express the smallest and tallest value for h, right? So we said that this was negative h divided by 2, this was h divided by 2 for these sort of y values, correct? Now, let's now think about the radius. And so the radius, you guys, on the one hand, we have this radius from here to here, right? And that r there. And this r here is for, this r here is for the sphere. So this is the r of the sphere, see? So let me just put here small letters, sphere. So that is for the r of the sphere. Now you have another r technically. You have another r that goes from there Actually, just to be a little more accurate, I guess the middle would be like IE to here. And so this R, which I will put R with an asterisk, okay, just to show that it's different. So this R is the R of the cylinder, okay? So, okay, how the heck can I express like the function, right, of the circle or whatever for the cylinder? So think about it this way, and this is like this is probably the biggest brain move part or thing that you have to do. See? So the integral that I use for the sphere looks like this. See? Now that comes from here, right? And this comes from the equation of a circle, where at the origin, you can express it like that. See? Now, this is for a y value that goes all the way up. So all the way up, this is for the sphere, right? So for the sphere, you have this y value associated to it. For the cylinder and the ring, actually, which is why we use those values, for the ring, it's a little bit smaller. And so the OG function has in mind, basically, the OG function has in mind this small, like, extra y values, right? Or these small extra y values. And how do they express it? They express it simply as y squared, see? And so all those extra sort of y values, they express it as y squared. But what is the y value that we are interested in for the cylinder? Only h divided by 2 or negative h divided by 2, see? And so really, if you follow the same sort of approach, because the cylinder in the end is also like very similar to a circle, it's just like topside down, right? You can actually express the function of the cylinder, right? If you rotate it by 360 a bunch of times and etc., the function of the cylinder is actually going to be square root r squared, so it's an extremely similar approach, right? Minus h divided by 2 squared. Ah, look at that. And so basically, this problem is super big brain because, I mean, my impression is that you have to know a lot of different stuff in order to go over this exercise. See? And so the biggest sort of jump or like specific thing you really have to know is associating that, okay, so if this comes from the equation of a circle, and because I have a smaller y value now, I can express that new y value as h divided by 2. Like basically this guy here. See? And well, you follow the process, it's y squared, so it's your y value, correct? You're just going to have it as um, h divided by 2 squared. See? So once you establish that, now you can plug that in for the volume of a cylinder, which is going to look something like this. It's going to be minus h divided by 2 minus h divided by 2 pi parentheses square root of r squared minus h divided by 2 squared. And this whole thing squared because we have our function squared, right? In respects to dy, right? Now, because, okay, these integrals are extremely similar, and in a certain way, it's not that they're the same, but they have both this, they have equal, I'm not expressing myself well. So the smallest value that they're going for and the biggest value, so the smallest with smallest and the biggest with biggest, are the same. And so when that happens, you can actually sort of combine these two integrals, and that way you can solve it all in one go. See? So this is just more of a work smarter, not harder sort of thing. You can combine these integrals, and yeah, you actually could have from the beginning just put an integral here and just done that whole thing. See? So maybe I should have done it that way. Whatever, who cares? You can combine these integrals. See? So because you can combine these integrals and they both have a pi that's in common, technically, right, what you end up with is a pi outside, the integral inside, right? And here, on the one hand, this squared with the square roots. makes you end up with, quite simply, r squared minus y squared, right? Minus, well, this squared affecting this square root, minus r squared minus h divided by 2 squared. So all of this in respects to dy. See? Now, because you want to solve smarter and not harder, you can keep on simplifying before you apply the actual integral. And so if you keep on simplifying, what you can end up with, well, on the one hand, you can actually do a big brain play and divide both sides by pi immediately. See? So you actually end up with 1 equals this whole integral. So this whole integral now is going to be da, da, da. If you go ahead and combine these terms, you're going to notice that this r is going to go away with this r, right? And everything else in between will stay the same. And because you have a negative with negative, this term on the right turns positive. See? So basically, you're going to end up with h squared divided by 4 minus y squared. And you're doing the integral of this in respects to dy. Okay? So how the heck does that even work? How does the integral work? Especially when you're putting the limits, right? From negative h divided by 2 up until h divided by 2. How does this look like what actually happens? So, well, I'm kind of running out of space here, so let me just rewrite it down here for a second. So 1 equals the integral from negative h divided by 2 up until h divided by 2 of h squared divided by 4 minus y squared dy. Now, for evaluating an integral, see, first you have to actually do the integral, and then you plug in like the lowest and highest values. See? So let me just write this on the side because the procedure is very important. So for an integral, first do the integral, which I know sounds kind of troll, like do the integration process, then plug in the highest value minus the smallest value, right? Again, this is just a very intuitive sort of approach or description. It's not the hardcore mathy way. First do the integral, like see what happens with the exponents and etc. Then do the highest value minus the smallest value. See, this is the part that like I really need you to understand because it's usually the confusing part. See, so first do the integral. Now you can go ahead and go to your formula booklet, and it should be here, right? So standard derivatives, standard integrals. All right, there it is. See? So the classic integral, which is the one that we're going to go through here, right? You don't have a logarithm in here. You don't have an e going around. You don't have anything wacky happening. So all you're really facing is the integral of an exponent. Okay? And so you can do the hardcore mathy way, which is looking at the formula booklet and looking at this, right? So this is the integral of an exponent. And all you really need to notice is that on the one hand, well, if you have x to the power of n, that means once you do the integral, you end up with x to the power of n plus 1, and you divide it by that n plus 1. See? So for example, if you have, I don't know, x squared, and you're trying to do the integral of this, you're going to end up with x 2 plus 1 divided by 2 plus 1. So you end up with x cubed divided by 3, which makes sense because notice, and this is more of a nerdy comment, but integral and derivatives are opposites. All right? Which is no different than like multiplying and dividing are opposites. Okay? So that means if you have, I don't know, 4x and you times it by 2, you get 8x, and you have 8x and divided by 2, you get 4x, right? And so this can be like an eternal sort of loop. The multiplying and dividing are opposites, and integral and derivatives are the same. So if you do the integral of x squared, you end up with x to the power of 3 divided by 3. But if now you do the derivative, all right, so derivative of this guy here, you end up with the 3 going back out in front, right? So you end up with 3x cubed minus 1 divided by 3. The 3 goes away with the 3, you end up with x squared. And so, interesting. Integrals and derivatives are opposites. this is worth mentioning because if you look at this and you have no idea how that works and it looks crazy and it looks nasty, you can also sort of big brain it and think about, okay, so think about it as a derivative but backwards. And you can solve it that way. You really can. Okay, I've met people that never fully understood integrals, but they did understand derivatives like to the brim, like very deeply, and they would just always think backwards. See? So I'm just saying, whatever floats your boat, do it. Okay? Now, here you have the derivative. I mean, sorry. ah, here you have the integral of an exponent. See? And just like the example I just showed, you end up with x cubed divided by 3. Here you have y squared, right? So for the integral of an exponent, you end up with this first term, actually. I'll explain in a second, but this first term actually ends up as like this, with a y next to it. And the next term ends up as y cubed divided by 3, right? You already explained that. Here I'm like full on, this is the first step, right, for doing the integral, right? So you do the integral and this is how you write it. You did the integral, you integrated it, and you gotta put down the lowest value and the highest value that you're going for, see? So that was like the first step, see, doing the integral. Now something that I forgot to explain is why a y appears here, see? So think about it this way. Imagine you have x squared plus 5x plus 3, right? And this is your function. And they tell you, okay, do the derivative of this. Well, pretty straightforward, right? So this 2 is going to go in front, so you end up with 2x plus 5, because here you have an x to the power of 1, see? Multiplies in front. And then you do minus 1, so you end up with no x. And this last term, right, is going to disappear. Because technically, here you have an x to the power of 0. 0 is going to multiply in front. 0 times anything makes it disappear. And so here's the derivative, right? Now, if you were to go backwards, right, so here we did the derivative. With my wonderful cursive writing that says derivative. If now you were to go ahead and do the integral, okay, to try to get back, there's two main things that we can learn here. So on the one hand, if you try to get back, yes, as we've learned, you end up with x squared for the first term, right? And notice, this term here had no x next to it in the derivative form. In the derivative form, it has no x next to it. That means in the integral form, it must have had an x next to it. Because anything, right, that in the derivative form does not have an x next to it, it means it must have had at least one. Or else, it would have disappeared like this one, okay? And last but not least, over here, you don't put plus 3 because you're not a psychic. Here you put plus c. And so, that is why we also put the constant when we do the integral. You put the constant because you don't know which numbers might have disappeared in the process. Interesting, interesting. And so the main thing I needed you guys to catch on to it is that if you have the derivative version with like a singular number by its own, that means that in the original one there must have been an x, or else that singular number would have disappeared like the 3. Okay, that is what I'm trying to tell you. And so from over here, once you do the integral, well, this does not have a y next to it, so in the integral version, it must. That's all it really is. See? And here you don't consider the plus c because you are evaluating it in like a minimum and maximum, right? If it were on an undefined integral, I think it's what it's called, when it doesn't have the boundaries, then yeah, you need to put the plus c. But in this case, because we're evaluating with actual numbers like this minimum and this maximum, you don't put the plus c. See? Now, how the heck does that work? This is the next step. Then plug in the highest value minus the smallest value. See? So I'm going to try to be as clear as possible. I'm going to put in dark green the highest value. So highest value is h divided by 2. So on the one hand, if you do the highest value, you end up with h squared divided by 4. And the highest value, you guys, enters right here into the y. It enters into the y's. And so the highest value is going to be right here, times h divided by 2. Minus, you guessed it, you have h divided by 2 cubed, damn, divided by 3. And so you do this, okay, you do this minus the smallest value, which we will be doing in pink, okay? And so the smallest value is going to be minus h squared divided by 4 times my smallest value is negative h divided by 2. Da-da-da, interesting. Minus negative h divided by 2 squared, cubed, divided by 3. So that is what I mean by highest minus smallest value. You first evaluate the integral with the highest value, subtract it to the integral evaluated on the smallest value. See? And so this looks absolutely crazy. It looks absolutely nasty. But there's one very important thing that just happened, you guys. Up here, and I really need you to notice this, okay? Because this is the cool thing about it, you know. This is why you do it. This is why we love it. Up here, how many variables did you have? You had h and you had y going around. But the moment that you evaluated, right, the integral with these h's down here, yes, it looks nasty. Yes, it looks crazy. Yes, no one wants to solve it. But the one good thing about it is that you have only h's. And so that is what helps you find the value of h. Finally, you found an equation, a formula, or a something that has only h on it. And so from here, you can solve for h doing a whole lot of math. So let's get excited about it. We're almost done. See? So this first parentheses, it's going to end up with h squared times h, so it's h cubed divided by 4 times 2, 8. Minus, here you have a cubed going around affecting both the numerator and the denominator, so you end up with h cubed divided by 8 divided by 3. I will show you how to solve that in a second, right? Minus, on the other side, you end up with negative h cubed divided by 8, so very similar to what we just had, minus, and this one is kind of crazy because you have negative h divided by 2 cubed, right? So I'm talking about how to solve this guy here, see? So because it's cubed, that means you have negative h divided by 2 times negative h divided by 2 times negative h divided by 2. And so on the one hand, it's pretty evident you also end up with an h to the power of 3, much like earlier, divided by 8. But because you have 3 negatives, it's an odd amount of negatives. So these, for example, turn positive, but then this positive is hit by that negative. Boom, you end up with a negative. So careful with that. So you end up with minus h3 divided by 8 divided by 3, right? And I'm just going to immediately show you guys, because you have a minus minus, really this is just going to turn into a plus. See? So careful with that. Small detail, very, very important. Now, you have a bunch of fractions, you have some big fractions, it's getting nasty, it's getting weird. What I suggest you do, okay, is write it as like a very big fraction. See, so you want to reach this. You want to reach this, one fraction on top of another. See, you don't like it when it's like that. You want it to be one big fraction on top of another. See? So from here, you can actually put it as h cubed divided by 8 divided by 3 divided by 1. Right? So this 3 divided by 1 is the same as 3. It's legal to write it this way. Trust me, guys, it's legal. No harm is being done. See? Minus the other parentheses, which ends up like this. So the same idea. Divided by 3 divided by 1. See? Now, this is just a personal approach. You can deal with fractions however you want. But my personal approach is that I like to reach the one fraction on top of the other because there's actually a very visual approach to solving this. To solve this, you can do a times d divided by b times c. Literally. See? The other approach that you can do it is you can technically say that it's a divided by b divided by c divided by d. And because it's a fraction dividing, what you have to do is the reciprocal. You've probably heard of that. It's a divided by b times d divided by c. But that's really the same thing that's happening up there. So you see, so a times d divided by b times c. Right? So it's the same thing happening. Use your approach. Deal with fractions however you want to. Yada yada. See? So now, we end up with 1 equals h cubed divided by 8 minus, well, this guy times this guy, so it's just going to be h cubed divided by 8 times 3, 24. Minus my other parentheses, which is negative h cubed divided by 8 plus, well, it's really the same thing, right? So plus h cubed divided by 24. And so from here, right, so from here, you can start like combining the fractions uh, right away. Is it better? Let me take a moment to think about it. I think it would be like a little bit better, I guess. So let's try to combine these fractions right away. So what they both have in common, when you are adding or subtracting fractions, you need the denominators to be the same. So when add/subtract fractions, you need the denominators to be the same. So because you need the denominators to be the same, you have an 8 on the bottom on the left, you have a 24 on the bottom on the right, and you can realize that 8 times 3 is 24. See, if you didn't notice that right away, just write on the side like multiples of 8. So 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24. Boom, you found something in common, right? So that means that if I amplify by 3, the fraction on the right, so you do times 3 over 3, that means they will end up with the same denominator. And once you have the same denominator, you can combine the terms more fluently, right? So over here, you're actually going to do the same, times 3 plus this guy, right? All right, so you end up with, oh, and this is legal. This is called amplifying, okay? Okay, I think I wrote that horribly. I think it's amplifying, see? It's legal because you're technically just multiplying by 1, you guys, see? So some of you might be thinking, don't you have to multiply by 3 to everything? I say, no, this is multiplying by 1. Guys, 2 over 2 is how much? 1. 3 over 3 is how much? 1. If you multiply a number by 1, for example, 101 times 1, it's still 101. So you're not changing it in any way. Yes, it's a fraction, you're changing how it looks like, but it's still the same number. It's still the same amount because you're just multiplying by 1. And so the word amplifying is kind of tricky because you might be thinking, it's getting bigger. Think about it like a magnifying glass. See? You're looking at an object, you're looking at it closer, you're looking at it farther. It's still the same object, okay? So, now that that's been established, this fraction turns into 3h cubed divided by 24 minus h cubed divided by 24. So this is my first fraction minus the other one, which is negative 3h cubed divided by 24 plus h3 divided by 24. See? So now we can finally sort of reach almost the last part of the exercise. It's been a long one, you guys. So anyone that's stuck around, you're a warrior, okay? You are a warrior. Good job. So the parentheses on the left, okay, it's going to be 2h cubed divided by 24 minus the parentheses on the right, which is going to be negative 2h cubed divided by 24. See? Now, because these two parentheses are separated by a small minus, this minus affects this minus, so really what you end up with is 1 equals 2h cubed divided by 24 plus 2h cubed divided by 24. So you end up with 1 equals 4h cubed divided by 24. So that means you can do times 24 to both sides in order to get h alone. This goes away with this. 24 equals 4h cubed. You want to get h alone, so divide by 4, divide by 4. H cubed has to equal 6. And how the heck do you solve h cubed equals 6? Well, you have to do the square roots with like a small little 3 here. This goes away with this. H equals that. Ladies and gentlemen, this is a very hard problem. Guys, that was crazy. That was actually like very impressive. This exercise is not the sort of exercise that is easy to notice what to do. I really try to focus on the thought process behind it, and the main tools that I think you should take home or write down or really just sort of like, that was very important, that was a huge step, is this guy here most of all. See? this guy here is huge. Okay. The other big thing that was surprisingly important was the equation of a circle. See, for understanding how your y is going to change, it was also a very big brain play that you had to notice, right? So, what was the thought process to even discovering that tool? Because it says rotated by 360 degrees, you should already be thinking about revolutions. And if you're thinking about revolutions, you're also thinking about the mark scheme. I mean, sorry, the the formula booklet and this guy here. See, I've noticed it's a classic of the AB, trying to find the volume of a 2D shape turned into a 3D and finding the volume. This is your main tool, you guys. Okay, this is probably the biggest sort of thing you can really write down and take home. It's this formula here. Don't fall into the trap of thinking, I have the formula booklet, so like I'm good to go. Guys, I assure you that none of you can tell me by memory what is inside the formula booklet because it's too much. And I'm not saying that you should be able to know what's in the formula booklet by memory, but you should know sort of what's in it. See? So that why is that important? Because the next time you're facing a crazy exercise like this one, and you read y-axis rotated by 360, you immediately think, rotated, revolutions. I know that's in my formula booklet somewhere. You don't have to know by memory which page. You don't have to know by memory like how it looks, how the formula looks like. You maybe don't even remember by memory how the formula works, but you know that it's in there, okay? And just that step is huge because then you open your formula booklet and slowly you start remembering how it works, where it is, etc., etc., and that gives you the big hint of how to move forward with an exercise like this. See, so the thought process oftentimes, you guys, depends on the buzzwords that they throw at you, the key formulas that arise from the formula booklet, and stuff like that. See? So, enough blah blah by me. Number 9 was pretty crazy. So, good job. Even for just trying this. Good job, you guys. Alright, that is number 9. I'll see you around, and I hope it helped.